Hi everyone, and welcome to my talk. Today I want to talk about cardinality estimation and some new approach to it. And this is a joint work with Oleg, who is also here present. So the talk today is about, about big data, but, have we ever cared about small data? So, big data is when we are, it's a buzzword. It's when we are talking about data larger than it fits on a single machine. And from a theoretical perspective, it encompasses models like streaming or massively parallel computing, or let's say distributed databases. So, if we are talking about, let's say, massively parallel computing, we can think of a situation where the data is distributed across many machines, and the distribution of the data, we can perform queries in the form that the queries are distributed and replies from the queries are gathered and accumulated on a single machine. Or we can think about streaming processing. So when we have conceptually an infinite stream of values or of records, and what we want to do, we want to sample process this stream in a small memory. That's, let's say, a single machine. So standard tool used in processing of big data is sketching. So by sketching, we can think of some summary of a data. So imagine we have a data set, and we just write some summary, some representation of this data, which is much compressed. I mean, this is extremely lossy compression because we are aiming really at gathering as much information as possible and compressing it as much as possible. So we don't think of some universal sketch, we think of sketch built for specific purposes, for specific problem we are trying to solve. And we have such sketch. Imagine we have a sketch built for specific type of queries. Well, we can just ask each of the machines in a, let's say, this distributed data set for a sketch of the data it contains locally. And then some aggregating machine can aggregate all of the sketches and compute some answer. Similarly, if you have a streaming processing, then we can imagine that a machine holds a sketch of everything it already seen, and it updates the sketch with every new element processed. So a problem, I think that's one of the fundamental problems in the area of sketching of big data, is cardinality estimation. So this is a problem where, as an input, we are just given a multi-set of values, and our query, our problem to solve is how many distinct elements are there. So here, for example, we have a multi-set of integers, and I mean, you have to think about it for a second to know that the answer is 10. And this actually, you can show that such a query, it requires us basically to store explicitly the answer, to store what is there in the multiset. So it requires a linear memory. This is something we really don't want to. But if we relax our problem, if we ask for some estimate, then this problem is actually much simpler. And as we'll see in a second, it's sketchable in really small memory. So our toolset in this problem, and this is a toolset used basically in every solution to this problem, is we pick a random hash function. You can think of a hash function as just a hash function from our universe to values of, let's say, to real numbers or to, let's say, infinite length bit strings. And with such a hash function, what we can do, we can apply it to each element and then worry about estimating the cardinality of the transformed multiset. Is it clear for now? Okay, I'm assuming there are no
like for me, obviously it is, right?
Yeah.
But
I need some feedback because I really don't see anything here. I just see the presentation. I don't even know if my internet connection is still on. So after applying a random hash function, we expect the hashes of different elements to be different and the hashes of identical elements to be identical. So the problem is still the same. What we gained is that we just randomized our input, and this is like we discarded the adversariality of the input. So we can think of, okay, let's just apply some hash functions, and then actually the schemes that we are going to consider, and this is basically this is followed by every scheme that I am aware of in this area, is that a sketch is just some observable. The observable is a function of already observed sketches, of already observed hashes of values that should be invariant to the permutation of order and invariant to repetitions. So for example, this is some very fancy words, but we can think of aggregating the smallest hash already seen, for example. So a sketch is some observable value of already seen hashes of the keys. And we hope to extract the cardinality just from the observable. So here on this picture, hashes are computed on the go and are discarded together with when we are discarding the elements of the stream. And the only thing we are going to store is the observable, which should be here, for example, a single value. And from this observable, we are going to extract the estimate. So to take a look at the related work of, or what is known already in cardinality estimation, from a theoretical perspective, most of the work has been put into something I would call epsilon delta algorithms, which are basically saying, okay, we want 1 plus epsilon approximation, multiplicative approximation of the cardinality, which is correct with probability 1 minus delta. And well, a long line of work shows that basically we can get down to logarithmic dependency in size of the sketches from n and delta. And there is this epsilon to the minus 2 term in the memory complexity. And the last work from Błaszczuk, it was Soda 2018 paper, essentially achieved optimal bit complexity. And the work already started in 1983 by Flashlat and Martin. I think someone wants to join. So work of Flashlat and Martin. This is like a textbook algorithm. It already gave us epsilon to the minus 2 log and log of 1 over delta bit complexity. And those algorithms are nice, but they are, especially the last two, the Kane, Nelson, Woodruff, and Błaszczuk work, they are quite involved, and they are actually sometimes involving huge constants and some complicated machinery, and are essentially not used in practice. So what is used in practice for cardinality estimation? Well, we have the variance-based algorithms, which on a high level, we say that such an algorithm uses some memory M, where M is, let's say, the number of registers we are using for the algorithm. And the standard deviation of the estimation should be of the order of n over square root of m. So this square root of m in the denominator is in spirit similar to this 1 over epsilon squared term that we had in the previous algorithms. Because we need this, I mean, if we want a standard deviation to be roughly of the order of epsilon n, m needs to be 1 over epsilon squared. So they are somehow comparable. And two used in practice algorithms were developed by Flageolet. I think there is a mistake in the authors of the HyperLogLog here, so disregard this. So basically, they use, let's say, m registers, but of log of the size of the universe bits, and they have a quite small standard deviation, so it's really almost in the order of n over square root of m. And actually, I went through practical implementation, and the HyperLogLog as an algorithm is implemented in almost all existing big data toolsets and distributed databases and streaming processing libraries. So how actually HyperLogLog or LogLog works? Those two I will be using interchangeably because they only differ in a small detail of averaging the output. Well, how do they work? They the observable we are going to use here is, if we take our element and we hash it, we just look at the number of trailing zeros. So the longest suffix that contains only zeros. So intuition is that with probability 1/2 there will be a single zero, with probability 1/4 there will be 2 zeros. At the end of the hash with probability 1/8 there will be 3 zeros, and so on. So if we just know the value of h, the maximal number of zero-only suffix over all elements of our multiset, then we can expect the n, the unknown value of the size of the cardinality, to be roughly 2 to the h. Because we know that, well, roughly if something happens with probability 1/8, it should happen roughly after 8 repetitions. So that is the intuition that I have here. So any questions for now? So how do we actually proceed from here? So if we have that, well, our estimate is, well, we just make some observable, which is 2 to the power of h, where h is some abstract value of the longest suffix of zero only that we have seen so far. Then, well, this is a very, let's say, coarse-grained estimation, because, I mean, the only values of this estimation are powers of 2. So this is not even close to the 1 plus epsilon estimation. So how do we proceed from here? Well, we repeat the same process independently m times. So input is pushed through m distinct observables, each of which aggregates over m distinct hash functions. And each of the observable produces some estimate on the value, and then we just average those values. So a single register in the HyperLogLog algorithm takes LogLog n bits because it only needs to store. I mean, if we think about it, what's the longest zero-only suffix in a random hash we are going to observe? Well, it should be roughly log n, or let's say 2 log n bits. It will be unreasonable to expect something more. So, I mean, if we want to store the number of bits at the end, well, we need only log n bits for this. So then the question is, which average is used in HyperLogLog algorithm? And if we use arithmetic average, it can be shown that it has some very bad properties. And in a LogLog algorithm, which was the first iteration of this approach, a geometric average is used. And in the HyperLogLog, which was a few years later, in 2007, published, they used a harmonic average. It can be also shown to be a minimum variance estimator in this problem. Any questions for now?
I'll just add that it's minimum variance unbiased estimator because
yes, right.
It's important that it's unbiased. Yeah.
So there is one more trick that you need to know about HyperLogLog, which is stochastic averaging. I think this is a very nice practical and theoretical trick. So for now, we have our sketch consisting of m words, each of them being very short. It's like LogLog.
If I might interrupt, a guy posted like a question on chat.
Yes.
Yeah. And I actually don't remember the answer. What is the maximum likelihood estimate?
Yes. What is the maximum likelihood estimator?
Yeah.
Yeah, I also don't remember. I only remember the term. Yes, so I think it's the question of if we condition ourselves on so the scenario is we are given some observables, and in this scenario we are looking at, let's say, observables which are taking the maximum value of some hashes. This is, let's say, a restricted scenario, but this is kind of isomorphic to what we are doing here. And now we are asked to design a function which, given observables, produces output, produces cardinality estimation. And this can be some arbitrary function. And the question is, can we actually? Yeah, I don't remember the precise definition. Sorry. Let's go back to this let's say at the end of the talk.
Yeah, but I also posted in a chat a very relevant paper that might be of interest if someone wants to dig deeper in that direction.
So I want to talk about stochastic averaging. So far, I mean, if we are given a new element in a stream, it needs to be pushed through each of the m hash functions and applied to each of the m observables. And then we are expecting the standard deviation to be roughly of the order of n over square root of m. So the trick of stochastic averaging is actually not to push each update through each of the hash function, but to do some preliminary hashing And on this preliminary hashing of our update, to put the key into only a single hash function and apply it to only that observable. So effectively, each observable receives only a fraction of the universe, because the hashing of which distributes keys to observables is pseudo-random. So the same key will be always hashed to the same observable. So each observable receives roughly n over m elements, and then from this we only apply updates to a single value. So this reduces the processing time to a constant time. And then, of course, we need to be a little bit smarter with how we compute the average, because everything is scaled down by a factor of m, but this can be resolved. So far, so good. So how actually is the HyperLogLog analyzed? So here, let me give you a quick glimpse of what actually goes on there. So Z here is the value estimator. And just to compute the expected value of the estimator, this is actually taken from the HyperLogLog paper. Well, we need to compute the expected value over all possible sketch configurations of the estimator and then of the probability of actually encountering such a sketch configuration, which still involves possible partitions of n, and then some distribution function, which, I mean, this is extremely involved. And this is the main contribution of the LogLog and HyperLogLog papers. And how do they achieve this? Well, this is a tour de force of analytic combinatorics. They had a very strong, a very heavy hitting hammer, and they use it. And I tried to went through the paper on many different occasions, and I only managed to get some very high-level glimpse into what's going on there. It uses some heavy tools from complex function analysis, like Poissonization and analytic depoissonization. The paper itself goes with half of the analysis through 10 pages, but then it includes Szpankowski's book on analytic chapter on analytic depoissonization. So this is truly involved work. And there are issues arising from this. I mean, because of this, we treat HyperLogLog as a magic black box. I mean, we know it works, and we have a proof that it works, but I mean, the proof itself for us is a black box. Because of this, I have a feeling that HyperLogLog is not truly covered in, let's say, big data courses or streaming processing courses, universities, as much as it could be. And because of this, algorithmic engineering involving HyperLogLog is hard, because there are some issues there that that needs to be taken care of, like fixing small cardinalities, fixing large cardinalities. And because of this, I think improving the algorithm itself, iterating over this, this is challenging. Any questions so far? Okay, I assume there are no questions, so let me proceed. So our contribution is, so what we propose, we propose smoothing of HyperLogLog by replacing a key component of it, which is coin flipping or geometric distribution, with a continuous equivalent of it. We propose a much shorter and elementary proofs of guarantees. The guarantees are of, let's say, epsilon delta flavor. And we also gather some insight on how to separate the effect of stochastic averaging from effect of observables. So I want to start with the HyperLogLog observable, which is maximal number of zeros at the suffix of the sketch. And if we look at how this observable is distributed after incorporating only a single element, well, this is a simple geometric distribution. So we have the geometric decay. And then imagine what happens if we look at the distribution after taking, after actually processing two distinct elements. So here we have a maximum of two values, each of which is distributed according to geometric distribution. And it has a slightly different shape. So there is a peak at value of 1. And then if we go further and further with more elements incorporated, more elements processed, well, the shape looks a little bit differently. So the shape does, I mean, maximum of let's say k geometric distributions is not distributed according to geometric distribution. It actually has a different distribution. So what happens if we let's say process 64 elements? I mean, it's not really clear to us what will be the distribution of it. Something involving 64th power of some terms here. So this is problem. If we have let's say values drawn according from exponential distribution, the maximum of them is not drawn from exponential distribution. But what can be observed is that in the limit, maximum of those, in the limit it goes to a different distribution, to a Gumbel distribution. So what is a Gumbel distribution? Gumbel distribution is also known as double exponential distribution. And it's a distribution arising from, well, extreme value theory. So it's a distribution that has this double exponential with negation dependency here. And what happens if we take a single value, and then let's say we take k different values from Gumbel distribution and take a maximum of those. So if we compute what is the distribution of maximum of k different values, well, after a little bit of computation, we can see it's the same distribution, but shifted by natural logarithm of k, which is still Gumbel distribution, just shifted. So if we plug it to the simplest possible algorithm in this area, what we do, we take each element x and apply a hash function. And let's say this time the hash is into value 0 to 1. Real values uniformly distributed between 0 and 1. And then each observable is just, we transform the value from 0, 1 to something distributed according to Gumbel. And then we take the maximum. And then we take the average. So what actually happens is that here, the maximums are also distributed according to Gumbel. And if we already processed n different elements, then the maximum is distributed according to Gumbel with a parameter log n. Any questions so far? Okay, let me proceed. So in this scenario, well, everything is just shifted by log n. So we can easily extract by geometric mean the estimate, because we can just take the average of the observables, subtract the expected value, and the expected value of a Gumbel distribution is the constant gamma, and we take exponent of this. And similarly for harmonic average, we can take the average of the exponent of the minus of the observable, and then normalize it actually there is no normalization there needed, and expect the harmonic estimate to work. So, I mean, this is the whole algorithm in the simplest possible form. And to see that it works, well, every xi in the first case is distributed according to Gumbel shifted by natural logarithm of n. The expected value of this is the constant gamma plus natural logarithm of n, and the variance is constant. Actually, it's p squared over 6. So by standard analysis, the average of all xi's will have the same expected value. So after normalization by subtracting gamma, it will have it. I mean, it will be concentrated around log n. And if we repeat it enough times, it will be additively plus minus epsilon, because we are just pumping down variance. So before exponentiation, we are additively within epsilon. So after exponentiation, we are multiplicatively 1 plus epsilon from n.
So I would just like to add, because I'm not sure if it was clear for everyone, that gamma is just Euler-Mascherani constant.
0.56 something.
Yeah, something. Yeah, because gamma, there are multiple gammas in different, parts of mathematics. So, yeah. That was this gamma.
Okay, and for the harmonic estimate, the story is the same. Xi's after n updates are distributed according to Gumbel shifted by log n. And now we can compute the expected value of those terms and variance of those terms. And by standard analysis, we can show that arithmetic average of those terms is 1 plus epsilon within k over n. So similarly, after inverting, we can show that z, our estimator, is 1 plus epsilon multiplicatively within n. So this concludes the first part, and for the second part, I think we will manage to do it in the next 5 minutes. So we now understand how it works just when we are pushing each update to through each of the observables. And how do we proceed with stochastic averaging? So we start by saying, okay, n items, and they are just partitioned according to multinomial distribution into k boxes. And in each of those boxes is an observable. And each observable is just a natural logarithm of the number of items that landed there, plus some Gumbel noise, because now we can think of it as a noise. For simplicity here, we are throwing one extra element into each of the boxes so that we never take logarithm of 0. So to analyze stochastic averaging, we are in a situation where each of the k values is, we have k values distributed according from n1 to nk by multinomial distribution. And then we are given k observables, where ith observable is just natural logarithm of ni, which is unknown to us. The ni is unknown to us. We don't know how the n was partitioned, and then it is shifted by some Gumbel shape noise. And then, if we are looking at let's say estimating the average of those, we are in a situation where the Gumbel noises are canceling each other, or let's say they are aggregating. And we are just averaging the natural logarithms of ni plus 1. So to understand how it works from a perspective of, let's say, geometric average, We just need to understand how this random variable y, which is just, let's say, average or sum of natural logarithms of ni, how it works. Because on top of this, we are just adding some Gumbel noise, which is of small variance after averaging over k steps. So we just need to show that, well, y will be roughly concentrated around its expected value or its common value. So informally, what we want to show is that y is concentrated around k log of n over k. Why log of n over k? Well, we have k values which are summing to n. On average, there will be roughly n over k. If we can show it that it concentrates around this value, we are done, because Gumbel noise will be of small variance, and we just need to know it's a small variance on top of what. So how do we show it? By convexity, we can upper bound the value of y. So by convexity, we can say that if we replace ni by its average, it will maximize the value. So y is smaller than k log of n over k plus 1. And how do we analyze it from the other side? Well, instead of looking at y, we can look at the expected value, but of e to the minus y. This is a little bit of a trick which comes naturally because y involves sum of logarithms, so exponenting it produces some product. And it actually is a product of 1 over ni plus 1. And this product can be actually analyzed from a point of expected value. This is a little bit tricky, but this is doable by high school math. And actually, it can be bounded that this expected value is just upper bounded by k over n to the power of k. And then if we have this, by Markov inequality, the expected value of the exponent cannot, I mean, the actual value of the e to the minus y cannot grow too much beyond its expected value. But because we are operating on the exponented side, it nicely translates to what happens to the actual value of y. For y to be smaller than a value of t, some abstract t, from k log of n over k, well, it goes exponentially into the expected value of e to the minus y. So it's the probability of such an event is e to the minus t. So roughly, we can say that, let's say, y will be at least k log of n over k minus 2 with, let's say, 5 over 6 probability. So this is a really nice concentration that we are achieving this. And if we have this concentration, we can already say that the expected value, that the estimation is nicely concentrated around n. So this concludes the proof. Any questions? Okay, let me just give some concluding remarks. So the proof that I just shown you on a previous slide, that was for geometric average. For harmonic average, the proof is basically of the same length, but for the time constraints, please see the paper. What we used actually, we used epsilon to the minus 2 real value registers for 1 plus epsilon precision. And I mean, this is a little bit of cheating because HyperLogLog uses integer registers, not real value. So the question is, how much precision do we need? Well, because everything is exponented, we can discretize everything to each of the real value to be only additively, to be within additive precision of epsilon. So the universe of our registers is of size log n over epsilon. So the registers are going to use log of these bits. And this is suboptimal because now we are putting epsilon term into the memory complexity. In fact, this can be improved, and we managed to get it down to log n bits, and it's still, I mean, there are no dirty tricks involved. It's just a little bit of extra ideas there. Thank you. Any questions?
Guy asks a lot of questions, and I wonder, okay, you don't have a microphone, right? Or is it like, because Przemek muted you? Okay, so yeah, there was this question, does the analysis rely on independence? And I think it does, right?
So the case of independence is really tricky. So in fact, it relies on us assuming we have perfect hash functions. And it's in theory, this is a problem. But this is the same problem for HyperLogLog and other related algorithms. And in fact, I think in a very recent preprint from Seth Petty, he just categorized the algorithms as, well, let's assume they have access to an oracle that is able to perform hashing for us. Does this answer your question?
Oh, that's a nice question.
Oleg, you need to read them because I don't see the question.
Yeah. Okay. Do you believe that one could design pseudo-random hash functions that are good for this algorithm?
I have no intuition here. I have no intuition. I mean, we don't need anything stronger than, let's say, HyperLogLog needs. We need hash functions which are independent with respect to taking maximum.
Because frankly, I don't remember how this is done in HyperLogLog. Because
it's not.
It's not. Yeah. Like in the original paper, probably it's not. There is obviously a series of papers regarding the practical aspects of HyperLogLog.
And none of those considers those. I mean, it's not an issue from a practical perspective. And I think it's a huge obstacle also from the theory side. I mean, I can understand why people are not assuming access to perfect hash functions, but this creates some other issues. I mean, I think it unnecessarily complicates the algorithms.
Yeah. So Guy asks what practitioners use.
There is this HyperLogLog++, which is implementation from Google. And this is just a HyperLogLog fixed with some different estimation for low cardinalities. Okay, I can see the chat now.
But no more questions. So.
Okay. If there are no more questions, let me just stop the recording.
Oh, guy tries to